All right, everyone, welcome. Today, we're going to jump into one of the absolute cornerstones of circuit analysis, the series circuit. Getting this concept down is, well, it's non-negotiable for everything that comes next in your studies. So let's get right to it.
So here's our game plan. We're going to start with the basics. What even is a series circuit? Then we'll look at how resistors link up, figure out how to calculate their total resistance, and, this is a big one, uncover the #1 rule about current. And, to wrap it all up, we'll put everything together and actually solve a complete circuit.
Okay, first things first, let's tackle that fundamental question. What does it really mean when we say components are in series? Okay, take a look at this. This is your classic textbook series circuit schematic. You've got your voltage source over on the left, right? And then look how those resistors are all lined up, one after the other. Now, it's super important to remember something. A schematic shows the electrical connections, not necessarily how it looks physically on a breadboard. What we care about is that single electrical path.
So, when you look at that, what's the one thing that just jumps out? What's the single defining feature that screams series circuit? Think about it. Think about the path that the current has to take. It all comes down to that single path. That's the answer. In a series circuit, there's only one road for the current to travel. It leaves the source, goes through the first component, then the next, and the next. There are no off-ramps, no forks in the road. It's a one-way street, and that is the defining feature. And think about what that means. If you get a break anywhere in that path, poof, the entire circuit is dead.
All right, so let's zoom in a little bit and talk specifically about how resistors are arranged within this single path.
Honestly, the best way to picture this is like links in a chain. See how they're connected? End to end. The tail of one component connects directly to the head of the next one. There's nothing else connected in between. It's just a simple, sequential link.
Okay, so we know how they're connected. Now we got to figure out what their combined effect is, right? I mean, each resistor is pushing back against the current a little bit. So what happens when you line them all up? What's the total opposition?
Well, this is one of those things in electronics that's actually really easy. To find the total resistance, you just add them up. Seriously, that's it. The combined opposition is just the sum of all the individual resistances. As far as the voltage source is concerned, it doesn't see a bunch of separate resistors. It just sees one single equivalent resistor.
All right, theory's great, but let's do a real example. Here we've got a 10-volt source powering 4 resistors, all connected in series. So job #1 is to figure out the total equivalent resistance. What's that one single value of opposition that our power source has to deal with? So, just like we said, we just grab the value of each resistor and add them all together. We've got 47 ohms plus 100 ohms plus 10 plus 56, and that gives us a grand total of 213 ohms. See? Just a straight-up application of that simple rule. Okay, resistance, check. We've got that handled. Now let's move on to the next major piece of the puzzle. And I'm going to say this is probably the most important rule you need to know for series circuits. It's all about how current behaves. Let's go back to that core idea. There's only one path, right? So what does that tell us about the current? Is the current flowing through the first resistor different from the current in the second one? Does the current somehow get used up as it makes its way through the circuit? The answer is a big resounding no. And this right here, this is the golden rule of series circuits. You have to burn this into your brain. The current is the exact same everywhere, at every single point in that circuit. The current leaving the power supply is the same as the current in R1, which is the same as the current in R2, and so on, all the way back. It is absolutely constant. So why is that? Well, it all goes back to a fundamental law of physics, the conservation of charge. Since there are no branches for the current to split off into, there's nowhere else for it to go. Think of it like a garden hose with no leaks. The amount of water going in one end has to be the same as the amount coming out the other. It's the same idea here. Every single electron that leaves the negative side of the source has to make its way back to the positive side. Okay, this is it. This is where we bring it all home. We know the total voltage from our source. We just figured out the total resistance of the whole circuit. With those two pieces of information, we can now find the one thing we've been looking for, the total current. And how are we going to do that? Well, we're going to call on our best friend in all of electronics, good old Ohm's law. Remember? Current equals voltage divided by resistance. And the key here is that we're going to apply this to the entire circuit at once. So, first up, we need that total resistance we already calculated.
That whole chain of resistors is acting like one single 213 ohm load to our power supply.
Okay, now we just plug and chug with Ohm's law. We take our total voltage, that's the 10 volts from the source, and we divide it by our total resistance, which we know is 213 ohms. That calculation is going to give us the total current for the entire circuit. And when you run the numbers, what do you get? 10 divided by 213 gives you about 0.0469 amps. Or to make it a little cleaner, we'll call that 46.9 milliamps. And now, don't forget that golden rule. Because this is a series circuit, that 46.9 milliamps isn't just the total current, it's the current flowing through every single component. Look, if you forget everything else today, just remember this simple mantra for series circuits. One path, one current. Add the resistance. That's it. There's only one path, so the current is the same everywhere. And to get the total resistance, you just add them all up. Lock that in. So, we've totally nailed resistance and current. But there's still one piece of this puzzle missing, isn't there? We know the source is providing 10 volts total. But what about the voltage across each resistor individually? How does that 10 volts get shared or divided up among them? Now that is a fantastic question, and it's the perfect lead-in to our next topic, the voltage divider rule.